Okay, well, I guess good afternoon at this point. Hi everyone. So my name is Mary Olsen. I'm actually currently a master's student at Coastal. I'm also an employee with the Environmental Quality Lab. So I'm here today to talk to you guys about my master's research because we incorporated environmental quality data and volunteer monitor data as well to work with my project. So I'm here to kind of present it to you guys because it's finished now and I actually graduate in 2 weeks. So end of the road. So our research was titled, it's a mouthful, Coastal Ocean and Estuarine Acidification in Long Bay, South Carolina, a comparison of in situ water quality monitoring with measured carbonate system parameters. And I would like to thank my advisor, Dr. Angelo Sanitas, for helping me along with this project. And I had many committee members as well. And our project was actually funded by South Carolina Sea Grant. They funded us to do this research as well. Maybe. So the first thing I want to talk about is kind of the basis of what ocean acidification is. So ocean acidification, or OA as I will reference it, is basically the decrease in pH due to the uptake of atmospheric carbon dioxide. Now, for most of you guys, one of the water quality parameters you guys measure is pH. And so when we look at ocean acidification in general, we can see with our image here that carbon dioxide is being inputted into our system with our yellow arrow up there. And so when that carbon dioxide from the atmosphere is then absorbed by the ocean, it then combines with the water, and then it produces what's called carbonic acid. And so this carbonic acid will then break up into a hydrogen ion and a bicarbonate ion. Now that hydrogen ion is going to determine pretty much the pH of the water. And so this excess of these ions are going to cause a decrease in pH, which is an increase in acidification, and it's going to cause a decrease in available carbonate. And that's going to be important in the future that I'll talk to you about. So overall, this uptake of that carbon dioxide is decreasing that pH in our water. It's making it more acidic, which is going to be detrimental to the water quality and our organisms that live there. So for ocean acidification, our ocean acts as this large reservoir for carbon dioxide. So right now, about 31% of anthropogenic carbon emissions have been absorbed by our oceans. And so this is looking at increasing carbon dioxide emissions. This will decrease the ocean's future capacity to absorb carbon dioxide. So the more carbon dioxide it absorbs now, the less it will be able to absorb in the future. So right now it's kind of being this, this sink for the carbon to be removed from our atmosphere, which is helping in terms of that, but it has to go somewhere. So it's causing detrimental effects to our ocean. And so this is seen when we look at pH. And so surface ocean pH has decreased from a value of 8.2 to 8.1 since 1860. Now, that may not seem like a very large decrease at first, but pH is on a logarithmic scale. So any changes that are happening are tenfold. So that 0.1 decrease is times 10. So it's much more significant than you might think right away. And so one of the things that this is concerning for is our marine organisms. So this is detrimental, especially to our calcifiers like corals and mollusks. So in this area, especially like our oysters. So they make their shells, their protective layers, their skeletons out of calcium carbonate. And to make those calcium carbonate shells, they need carbonate in the water. And so with a reduction in that, they do not have the availability to make those shells. And so it becomes difficult for them to make their shells and form those structures that provide that protection for them. So now we're going to look a little bit of a step further. So we're going to look at coastal ocean and estuarine acidification. So ocean acidification is more in terms of open ocean, global ocean, wide with just atmospheric emissions. However, there's a step further, and we actually, with such a populated area on the coast, this is one of the things we wanted to look at. So because of an increase in urbanization and adding impervious surfaces to our coasts, we have all these buildings and roads and a lot of surfaces that rainwater can run off from. So this is a diagram with a lot of complex processes that are affecting this coastal ocean and estuarine acidification, but it's more of a localized effect than just that global effect. So we have things that are affecting our carbonate system, like nutrient runoff from our surfaces, that agriculture nutrient inputs, they run off into our rivers and our coastal waterways and to our estuaries that then lead out to the open ocean. We end up having transport from our marshes to our open oceans as well. Wastewater facilities, agriculture, factories, things like that are all pieces to this carbon story of our area. It's the story of a localized area. And so one of the things as well that a lot of you know, we have highly organic rivers. We have blackwater rivers around here. So organics can affect our carbon system as well. And so that's one of the things that need to be looked at as well. So while open ocean acidification is that more global, this is what we're going to be referring as, and this is more of our localized that has more than just atmospheric carbon dioxide affecting. We have other processes that are going to be affecting that system. So pH scales. So there are actually 4 different pH scales that are commonly used in seawater measurements. Now, for the basis of this project, we looked at 2 different scales. So the first scale is the total hydrogen scale. That's the PHT scale. And this is the globally accepted scale for acidification monitoring. Now, the scale that all of us measure on with our data sons and things like that when we take our measurements is called the National Bureau of Standards scale, and that's the PHNBS scale. And so this is typically used by handheld meters and sons. And so this is not the globally accepted scale for acidification monitoring because we want more decimal points to look at those small changes in acidification. And on the NBS scale, we only go to 2 decimal points. So when comparing these, the relationship as well between the 2, you can't just go back and forth with them because it's not a straightforward relationship. They measure two different things. Our total hydrogen scale is accounting for bisulfate, which is important because we're looking at seawater. And so this is our pH scale and acidic, neutral, and alkaline. Okay, so now we're going to get into kind of the carbonate chemistry a little bit, the different parameters. So the first 2 that I would like to talk to you guys about, we're looking at our calcium carbonate, that's CaCO3, saturation state minerals. And so we have 2 different types that are commonly used, and that's our aragonite saturation and our calcite saturation. And that's normally represented by that omega symbol, is the saturation state. Now, marine organisms secrete calcium carbonate, and they do it primarily in those 2 forms, aragonite and calcite. And so aragonite is about 50% more soluble in seawater than calcite. So with this rising ocean acidity, aragonite shells are actually expected to dissolve first than calcite since it's more soluble. And an aragonite saturation of less than 1 is seen to be undersaturated, and that's where our shell dissolution will happen. So we'll see that dissolving of those shells because they don't have enough carbonate to make those shells. However, we actually see that detrimental effects to these organisms can be seen above that saturation state equaling 1. And so Rockstrom et al. Actually in 2009 set a boundary of anything less than 2.75 we can see detrimental effects to organisms. And so I provided some examples of organisms that use these minerals to make up their shells and skeletons and protective barriers. And so One of the really important ones for around here is going to be our oysters, right? We have a lot of oysters around here. So that's one of the ones we want to be concerned about. So 3 other parameters that we looked at, because the carbonate system is a pretty complex and it has different pieces to it. So the next one that we looked at is dissolved inorganic carbon, or DIC. And so this is the sum of inorganic carbon species within the water, and it is the total carbon dioxide in our seawater. And so in seawater, DIC mostly exists as carbonate and bicarbonate ions. Now, the next parameter we look at is total alkalinity, or TA. And so the basis definition of TA is that it's the excess of proton acceptors over proton donors relative to a reference point. It's also known as the buffering capacity. So it's what's going to offset that carbon in the water. And then PHT, again, is our globally accepted scale for acidification monitoring. And this is due that it accounts for the concentration of the free hydrogen ion, along with the one that dissociates from hydrogen bisulfate. And that's because of a high sulfate concentration in seawater. Okay, so kind of finished with our background information. So now kind of getting into the research. So the study objective for this project was to, 1, provide the first characterization of temporal scales of coastal ocean acidification in Long Bay, South Carolina. And this would be done through the leveraging of long-term data sets at both coastal and estuarine sites. So we were looking at data sets from 2 coastal piers and 2 of the volunteer monitoring sites. Then we were looking to validate these decade-long data sets gathered using sensors through the discrete sampling for DIC and TA. And then to finally show that water quality parameters as monitored by these sensor technologies can be used for coastal ocean and estuarine acidification assessment. So our hypotheses for this project including the following 4. So we wanted to see if the relatively low accuracy but high temporal frequency pH NBS, which is collected by the sensors, if those could be used at all 4 sites in Long Bay, South Carolina, as a proxy for our pH total scale, which is that globally accepted pH property for acidification monitoring. And so this was to see if pH NBS from our sensors would have a 1-to-1 relationship with pH total that we were going to calculate. And then 2, that 2 coastal ocean and 2 estuarine sites in Long Bay, South Carolina have been experiencing decreasing pH and degree of saturation of calcite and aragonite over the past decade. And so this relied on the fact that total alkalinity would have a direct relationship with salinity in addition to pH being used as a proxy. 3, then that the estuarine sites are actually more prone to acidification than the coastal ocean sites. And 4, finally, that pH at our study sites co-varies with temperature, dissolved oxygen, and salinity, specifically having an inverse relationship with temperature, a direct relationship with dissolved oxygen, and co-varying with salinity. And so those are all parameters that are also collected at the sites as well. So the study sites for this project included 2 coastal ocean pier sites, which are monitored by the Environmental Quality Lab at Cherry Grove and Apache Pier. And then 2 sites from the Murrells Inlet program at Oyster Landing Beach and Rum Gully Creek. And so both of these sites have sensors that are used. The piers have in situ deployed. They monitor and collect data every 15 minutes. And then you guys sample at our Murrells Inlet sites bi-weekly. So the field sampling for this project included the collection of 120 discrete samples in total. And so you can see the bottles that were used to collect in the image. And so that's the bottles that we used, we filled for our samples. And so these samples were collected contemporaneously to the ongoing routine observations at the sampling location. So we went out with the sampling schedule and we sampled right next to the volunteers as they were collecting their samples. And we did that in what's called a Niskin bottle. It's hard to see in that image. I think there's a better image further, but it's this giant gray bottle that will sample the water, and then we use tubing to subsample it into our bottles. And this was important because we didn't want any atmospheric exchange with the bottle, so we didn't have any carbon dioxide from the atmosphere getting into our samples. We just wanted the chemistry of the water itself that we sampled. And so then these samples were preserved with saturated mercuric chloride, and this was done to prevent any biological activity that could alter the chemistry of the samples, like respiration or photosynthesis. And so this sampling was performed from July 2022 to February 2023. That should be 2023. Now at Cherry Grove Pier, it is important to note that we only sampled from July to September due to Hurricane Ian. I think everyone can remember that hurricane. He ended up damaging the middle of Cherry Grove, and we were no longer able to get out to our sampling station there. So samples were, once 120 of them were collected, they were then taken to Moat Marine Laboratory in Sarasota, Florida. I actually drove 120 of them down in coolers in a car. And I spent a couple days there where I got to learn how to analyze the samples for total alkalinity and dissolved inorganic carbon. And then for the rest of the time, their technicians analyzed our samples, and a few months later, we received the data from them. And so these are some images of the equipment that is used to run that analysis. So now we had, a sheet with a bunch of data and numbers on it. What are we going to do with it? Because we only had dissolved inorganic carbon and total alkalinity, but our carbonate system has many more parameters with it. Well, someone created this really cool program called CO2sys, and it's a program that's used to calculate carbonate system parameters. So we inputted dissolved inorganic carbon and total alkalinity, and then also the temperature, salinity, and depth from our sensors collected at the same time. And from those values, we were actually able to calculate partial pressure of CO2, which is PCO2, our hydrogen ion concentration, pH on the total scale, and our saturation states for aragonite and calcite. So with those two parameters that we analyzed for and the sensor readings, we were able to calculate the rest of the carbonate system. So now looking at some of the data that we got out. So this is actually data from Oyster Landing and Rum Gully Creek that our volunteers collected for us. So one of the parameters we calculated, we had analyzed, was dissolved inorganic carbon. So this is a time series of dissolved inorganic carbon on our y-axis, dissolved oxygen on DIC on the left, dissolved oxygen on the right, sorry. And then collected over the full span of sampling from July to January. And so we have our dissolved inorganic carbon with our closed triangles and dissolved oxygen with our open diamonds. So one of the things that I wanted to point out that we kind of found out through looking at this data is one of the processes that could potentially affect our carbon in the water is primary production or photosynthesis. So when photosynthesis happens, we have our sunlight and our oxygen increases from our primary producers, and they're producing oxygen and they're taking up carbon. So we see a removal of carbon in the system. And so looking at this data set, highlighted in the yellow bars, we can see some instances where we have that higher dissolved oxygen coinciding with a decrease in dissolved inorganic carbon. So this is a process that could potentially have been affecting our carbonate system outside of just that global uptake of atmospheric CO2. So this is one of those localized processes that could be affecting our system. Now, looking at kind of the opposite of that, respiration. So at night, our primary producers are actually producing carbon dioxide, and oxygen is being taken up. So we see an increase in carbon and a decrease in dissolved oxygen at these sites as well. So now looking at two of the parameters that we calculated. So these are box plots. So these represent the ranges for the entire sampling period, with the middle of the box being our median value for the entire sampling period. So the volunteer monitoring sites are our green and our purple boxes. The green is Oyster Landing. The purple is Rum Gully Creek. And so we're looking at partial pressure of carbon dioxide and pH total. So that's the pH scale that we calculated. And so one of the organisms I really wanted to look at to see if we were having detrimental effects was our eastern oysters, which are the ones that are readily found around here. And so a study in 2014 found that oysters exposed to partial pressure of CO2 of value 750 and above were seen to have detrimental effects like thinner shells, slower to metamorphose, and increased rate of predation due to being more vulnerable. And that was also a pH of 7.93 and below. So we can actually see that our estuarine sites are encompassing those ranges. So that's indicative that these organisms could be experiencing stressful conditions, and this may be affecting them in our areas. And so then also looking at our calcite saturation state and our aragonite saturation state, the same study found that the oysters exposed to calcite 2.82 and below and aragonite 1.83 and below saw these detrimental effects. So again, Rum Gully Creek, we are starting to see values that are below these. So this is indicating that at these estuary sites at Murrells Inlet, we could be seeing water quality events that we are having detrimental acidification events for these organisms. So now getting into one of the really cool things from this project. So one of our first hypothesis, we were looking at comparing pH NBS, which was our sensor read pH, to pH total, which is the pH that we calculated. So at our peer sites, we actually found that we didn't have very strong linearity, but I would like to say that the Murrells Inlet sites actually showed very strong linearity, which was really impressive. So your pH data held up very well. Very well. So we can see that we have a fairly, especially at Rum Gully Creek, we have almost a perfect relationship between the two. And so that indicates that with the current methodologies that you guys use and the current sensors you guys use, that this data could potentially be used to look at acidification trends. Now, one of the limitations with this, and hopefully future studies will help put a more information and kind of solve this story a little bit. One of the things we looked at was total alkalinity versus salinity. Now, in the open ocean, total alkalinity is seen to have a linear relationship with salinity due to it strictly being affected mostly by precipitation and evaporation of water. Now, at all of our sites, we failed to see that relationship. So that's just telling us that there's something else going on and we have to investigate that further. And then looking at our data with covariance with other water quality parameters collected, we can see that at our volunteer monitoring sites in the green and the purple, that with temperature and dissolved oxygen, with temperature, pH showed a strong inverse relationship. So as our temperatures decrease, we see a decrease in pH as well, or an increase, excuse me, sorry. And with dissolved oxygen, they have a very strong linear relationship. So that's telling us that we see low pH events with low oxygen events. Okay, so kind of to sum all of that up. So with our pH versus pH, our estuarine sites showed that we can use that data as a proxy for pH total, which is really good news. However, with that lack of a linear relationship between TA and salinity, further information is needed. And this is just due to that carbonate chemistry is more complex and more dynamic in these coastal ocean estuarine acidification areas. And so this could be due to the fact from biogeochemical processes, especially respiration, like I showed you previously. We have riverine inputs from those highly organic rivers, terrestrial runoff. We have groundwater affecting the areas, ocean surface currents. So all these different pieces play a part of the puzzle, and we just need to start fitting them. And then one of the things that I would like to look at in the future too, it's called organic alkalinity. And that's just briefly organics that are going to affect the total alkalinity of the system. So future studies, there's a need for more observations and sampling to detect these potential acidification trends. And we would like to identify these key biogeochemical properties, especially nutrients, and chlorophyll A would be really interesting to have as well. And then potentially do direct measurements of pH total instead of calculating it, trying to measure it directly. And then also accounting for that organic alkalinity due to our blackwater rivers and our saltwater marshes, which are pretty highly organic around here, and looking at these seasonal variations that may be happening. And then briefly, just wanted to, I've presented this on a multitude of platforms, so this data has seen many audiences, presented on to teachers, local conferences, to municipalities. I actually was in New Orleans in February at Ocean Sciences International Conference, so this was done on a large-scale oral presentation at an international conference, so this data has seen many audiences, and I just really want to thank everybody for their help, and we really appreciate all that you guys do. And so acknowledgements, there's a lot, but I want to thank our volunteers that helped us, as well as our funding, our collaborators, advisory committee members, and my student. And with that, I think I'm out of time.